base case reproduction number, or the R0. So let's move this up and let's get to it. Right then, what it is the average number of secondary cases per case, and it's usually described as the R0. So you normally go and think about it as a network analysis, a big web. Who infects who? So I'd like to go and make this point. So it is used to measure the transmission potential of a disease, and I can't stress enough the red word there, potential, because it assumes that every person in the population is susceptible, which normally isn't the case. It is essentially something completely new that we've got no acquired immunity from, and certainly no vaccinations. This is quite a huge assumption to go and work with. However, it does work quite well with novel diseases, so the things that are introduced new to a population, which have quite devastating effects. Examples can be COVID-19, Ebola, Spanish flu, or smallpox. Smallpox, Spanish introduced it to South America, and it completely wiped out the natives' population, decimated them. They didn't even need to fight. So novel diseases, this is quite a dangerous thing when you're actually talking about novel diseases, but in most cases the R0 can't really be used because these are a dime in a dozen. You don't really go and get very many of them. So R0, if it equals 1, then the disease is stable in the population. It's not increasing to an epidemic, but it's not going away. It's what you call endemic. If it's greater than 1, so R0 greater than 1, the disease is increasing in the population. It can become an epidemic if it carries on. So you need to roll out interventions. R0 being less than 1 means that the disease is decreasing and your interventions are working. The disease is dying out. So if it carries on at that speed, then it's going to be completely eradicated. So what is it? It is dependent on 3 variables. Now this is really important. It is dependent on the duration of the infectiousness. Some diseases have different infectious periods or shedding periods, and different points in time where their individuals are even are at higher risk, so are after death for Ebola cases. Hence why the burials and the washing was such a contributing factor to the spread of Ebola. Another is probability of getting infected when exposed, so the almost viral dose, how likely you are if you're exposed to an individual who is infected, you are of getting said infection. And the average rate of contact amongst the population. Now, you can separate these into 2 areas. So you've got the first 2. This is life cycle and the biology of the pathogen. That is pathogen dependent, right? However, the average rate of contact amongst the people, this is behavior of the host population. And normally when we're talking about host population in infection models, etc., we're talking about us. We're talking about the humans. And because it's us, we have and because we're so different in different parts of the world, and we have different cultures and different practices and different behaviors, this means that the R0 number will change area to area. So then, I'll give you a visual here. So we've got 2 individuals. We've got 1 individual, and he's infected 2 others. And these individuals that individual's infected another 2, and then another 2. This makes the R0 2. So it's 2 plus 2 plus 2 divided by 3, which is 2. This individual infects 3. Another 3, another 3, another 3. You've got 3 plus 3 plus 3 divided by 3. So 9 divided by 3, which is 3. R0 is 3 in this population. Remember, this is population dependent, and it can vastly differ in different cultures. So this is really difficult in practice, and it takes a huge amount of effort to go and actually start figuring this stuff out. And it has it has a lot of errors within it because it's so dependent on everyone being susceptible to the actual infection, and you can't fully state whether an entire population is susceptible, because you can go and get odd anomalies, odd quirks, especially with new diseases. So COVID-19, the information is sparse, so we don't actually know at the moment what. Well, there's research going into it, but we're a little bit. Yeah, information's very sparse. However, hospital outbreaks of this are actually quite a good measure, because you've got a lot of data here. You've got quite a lot of accuracy in the data, and precise data also, quite detailed, because you have bed numbers and you have time of onset illness, so you can be you can work this out with quite a high degree of accuracy. Now, you may wonder how to calculate this for the population, because it's situational dependent, and you can't, a lot of the time, you can't afford the resources to go and be counting everything and looking at everyone, right? And contact tracing for everyone. Sometimes, especially with the COVID-19, there's just so many. So how do they work it out? So, this is where the secondary attack rate comes into play from before. Now, you can calculate the R0, especially with the COVID-19, by having the secondary attack rate of a household times the number of contacts within that household. Then you add that to the secondary attack rate of the individuals, so you go a bubble out, the drop-ins, people who drop in, times the number of contacts in the drop-ins, and then you add in the wider population. You keep going wider and wider and wider, and you go and take your subsample and you try and infer from that population what the attack rate will be, right? So we already know our cases, so now we can contact trace for their family, and then we can use our secondary attack rate. We can find all of this out, and then we can go and actually take a number from what we've got, from the amount of resources that we've been able to go and secure, and actually calculate this, and actually go and track, contact trace all of these individuals. We can actually infer a secondary, a R0 from this. However, I would like to mention that because each area around the world have slightly differing behaviors, have differing control measures for the infection, it means that the R0 will be different. It will be slightly, there will be a difference in each country, because the cultures are different. There will be something, no matter how small it will be, but there will be differences. And also because the control measures are different. So yes, I hope that has put in mind. Now the base case reproduction number, it can be estimated using a far more complicated method, and that's likely that's definitely how it has actually currently been done. And it is heavily statistically, a huge chunk of algebra. I will go over that at some point, but I need to learn it myself. So that is currently my knowledge of base case reproduction number. Over and out.